So question 5 from September 2013, MEC241. A water supply system for a building is shown in figure Q5. The vertical distance between point 1 and point 2 of the water supply system is 50 meter, and the flow rate of water being pumped to the tank of the roof of the building at point 2 is 750 liter per minute through a 60 meter long and 100 mm diameter galvanized iron steel. The power delivered by the pump is 2000 watt. So first determine the Reynolds number and flow condition in the pipe. And second, the friction head loss in pipe. Third is the minor head loss in pipe. And for the pressure at point 1 of the water supply system. So given the minor losses coefficient of the fittings used are K entrance 0.5, K exit 1, K globe valve 1.9, K check valve 3, K 90 degree elbow 0.9, and K pump is 1, is 6. And then so Reynolds number. So first question is Reynolds number. So Reynolds number equal to rho Vd over mu, or Reynolds number equal to Vd over kinematic viscosity. So we have to convert the units of volumetric flow rate from liter per minute to meter cube per second. So Q 750 liter per minute times with 1000 liter is equivalent to 1 meter cube, and then 1 minute is equivalent to 60 seconds. So you can cancel out the units, and then you get 0.0125 meter cube per second. So that is your Q in meter cube per second. So to find the velocity, so you have to use the equation Q is equal to UA. So U is equal to Q over area. So area of the pipe is equivalent to the equation used is pi d squared over 4. So pi times with the diameter of the pipe is 0.1 square over 4. You will get the value for area is 7.85. 4 times 10 to the power of minus 3 meter square. So substitute the value into the equation. So U equal to 0.0125 meter cube per second divide with 7.854 times 10 of minus 3 the square. So you will get your velocity is 1.5915 meter per second. So substitute into the equation, Reynolds number equation. So Reynolds number is Vd over kinematic viscosity. So velocity is 1.5915 meter per second times with diameter is 0.1 meter divide with kinematic viscosity is 1 times 10 to the power of minus 3 meter square per second. So you will get the value for Reynolds number, which is equivalent to 159,150, or 1.6 times 10 to the power of minus to the power of 5. Sorry. So this is a turbulent flow. Next is to determine the friction head loss. The friction head loss in pipe, or in other words, we have to determine major losses. So to determine major losses, we will use Moody's chart. So to determine the friction factor, so the first step, you must know the value for Reynolds number. So you already get the value for Reynolds number in your first question. So second is relative roughness. Relative roughness is equal to epsilon over diameter. Epsilon is absolute roughness, and then D is the diameter of pipe. So the absolute roughness for galvanized steel pipe is 0.15 mm. So substitute into the equation, 0.15 mm divide with 100 mm, so you will get 0.015 mm. Oh, I'm sorry, no units. Sorry, 0.0015 for relative roughness. So from Moody's chart, value for F is equivalent to 0.02141. So what you have to do is to substitute into the equation, HF equal to FL rho V squared over 2D. So your friction factor is 0.02141 times with length of the pipe is 60 meter, and then the rho is 1000 kilogram per meter cube, and velocity is 1.5915 meter per second square, divide with 2 times with 0.1 meter. So you will get the value for the major losses is 16268.6384 meter. Okay, this is for HF, major losses. So third is minor losses. So we have one entrance, one exit, one globe valve, one check valve, 3 90-degree elbow, and one pump. So the equation used is HF equal to KV squared over 2G. So H minor equal to 0.5 plus 1.0 plus 1.9 plus 3.0 plus we have 3 quantity of 90-degree elbow plus 6, which is 1 units of pump, times with 1.5915 meter per second square, divide with 2 times with 9.81 meter per second square. So you will get the H minor equal to 1.9494 meter. So H minor. So we move to the fourth question, which is to determine the pressure at 1. So to determine the pressure at 1, we have to use Bernoulli's equation. So from Bernoulli's equation, P1 over rho G plus U1 square over 2G plus Z1 equal to P2 over rho G plus U2 square over 2G plus Z2 minus H pump plus HF. So HF is a summation of major losses and minor losses. So rearrange the equation. So P1 over rho G equal to P2 over rho G plus U2 square minus U1 square over 2G plus Z2 minus Z1 minus H pump plus HF. So first we have to determine the value for the H pump. So to determine H pump, so we will use work pump equation, which is work pump equal to Q rho G H pump. So H pump equal to work divided with Q rho G. So substitute all the equation. So we already know the value for the work pump, which is equivalent to 2000 watt. So H pump equal to 2000 watt divided with 0.0125 meter cube per second times with 1000 kilogram per meter cube times with gravity 9.81 meter per second square. So H pump is equal to 16.3099 meter. So velocity at point 2 is equal to 0 meter per second. Why? So let's look at the example below. So we have one small pipe entering a tank. Okay, flow rate for the small pipe with diameter 1 and entering tank, which tank has a diameter D2. So if the diameter of the pipe D2 is relatively larger than D1, velocity at point 2 will approaching to 0. So how? So velocity at point 2, this is point 1 and point 2. Then velocity at point 2 would be 0 meter per second. So how? So let's take a look at the volumetric or discharge rate equation. So volumetric or discharge rate equation. So Q equal to UA. So U equal to Q over area. So let's say if the tank with a diameter of 0.1, if D2 is equal to 0.1 meter. So D1 equal to 0.1 meter. What if D2 equal to 0.1 meter? So the velocity at point 2 is equal to velocity at point 1, because it has the same diameter, which is equal to 1.5919 meter per second. So but what about the tank with diameter of 2 meter? If D2 equal to 2 meter, so by using this illustration, we assume that we must make that Q, volumetric flow rate, constant. Volumetric that flows into the tank, constant. So the difference is in area. So if D2 is equal to 2 meter, so we calculate that over, so the area is pi E squared over 4 . So you will calculate the value. So you will get 3.979 times 10 to the power of minus 3 meter per second. So, or equal to 0.00397. So here it can be seen that with a diameter of 2 meters, the velocity of water in the tank is equivalent to 0.03979, which is approaching to 0. Therefore, tanks may not have a diameter of 2 meters. It might be more than that. Therefore, we can say that U2 is actually equal to 0 meter per second. So for the U2, so we can cancel out the term U2 here, which is equal to 0. Okay. So next we move to the elevation. So we move to the elevation. To determine the elevation, you must determine the datum line. So the datum line might be Z1 at point 1, which is Z1, or at point 2, which is Z2. But you don't have to worry, because if you select Z1 as your datum line or Z2 as your datum line, both of them will give the same result in terms of elevation. So let's say I chose Z1 as datum line. So let's take a look at the picture. The the figure. So I chose Z1 as my datum line. So Z1 is equal to 0 meter. So at point 2 is elevate at 50 meter positive. So this is 0 meter, and if we draw the y-axis here, whatever values that is greater than 0 meter, 0 at y-axis, so it will give positive value. So Z2 is 50 meter. Okay, so we substitute into the equation Z2 equal to 50 meter. So we know that in the Bernoulli's equation, Z2 minus Z1. So Z2 is 50 meter minus Z1 is 0 meter, our datum's line. Therefore, it will give you positive value of 50 meter. Okay, the elevation. So Z2 minus Z1 is delta Z. So what if I chose Z2 as my datum line? So Z1 equal to, so take a look at this figure. So I chose Z2 as my datum line, so it would be 0 meter. So if we draw y-axis here, I'm sorry, this is not straight. Y-axis, so whatever values that is below than 0 meter, 0, it will give you negative value. So here Z1 position is negative 50 meter. So substitute into the equation negative 50 meter. So delta Z equal to Z2 minus Z1. So substitute to the equation, Z2 is our datum line, will be 0 meter minus 50 meter for Z1. So we will get 50 meter. So that is why, as I mentioned before, either you choose Z1 as your datum line or Z2 as your datum line, it will give you the same result. So here I will choose Z1 as datum line. So P1 over rho G equal to P2 over rho G minus rho U2 square over, sorry, not U2 square, U1 square plus rho G Z delta Z. I make it clear, rho G delta Z minus H pump rho G plus, sorry, I'm sorry, this is wrong. So P1 over rho G equal to P2 over rho G minus U1 square over 2G plus delta Z minus H pump plus HF. So multiply both sides with rho G to cancel out rho G. So P1 equal to P2 minus rho U1 square over 2 plus rho G Z2 minus H pump rho G plus HF rho G. So substitute all the information to get value for P1. So P1 equal to, P2 is P at PATM because it is exposed to the ambient, exposed to ambient. Therefore, the ambient pressure is PATM, equivalent to PATM. So we say that P2 is equivalent to PATM, which is 101.32 times 10 to the power of 3 Pascal. So you don't have to worry about the Pascal. Pascal unit is equivalent to Newton per meter square. So minus, kilogram per meter cube meter per second square over 2 plus minus 1000 kilogram per meter cube times with 9.81 meter per second square not divide, plus 1000 kilogram per meter cube times with 9.81 meter per second square times with 8.6384 plus plus 1.9494 meter. So P1 is equal to 160.045.019.7 Newton per meter square or Pascal, or you can equal to 160.05 megapascal. So you already solved this question. Thank you.